keratoconus.
All right, thank you. I want to thank the organizers and particularly Terry for inviting me to participate in this meeting. So what I want to do is give you a foundation so that you understand what's new and where we can go. And I want to even add a little bit to the previous presentation by my friend Minto. So in keratoconus, biomechanical alteration is the first thing that happens. So curvature, thickness, elevation changes, those are all secondary symptoms of keratoconus. The first thing that happens is a focal biomechanical change. Now let me show you what I mean. If you look at the, and I'll talk more about stress-strain diagrams tomorrow, but if you look at stretch versus stress, and you can think of stress as IOP, a stiffer material stretches less than a material that is less stiff. So if you look at the anterior surface of the cornea and you think of one area weakening, a focal weakening, it's going to stretch more. And as it stretches more, the cornea's response to that is to increase curvature. And that's what drives then this focal increase. So if we have a focal reduction in modulus, it changes the stress distribution, it causes thinning and stretching in that one area, which redistributes the stress distribution, which causes increased curvature. And there's a cycle that leads to progression in keratoconus. So you have this constant changing stress distribution. Now, this focal change is also evidence of this is provided by Keith Meek, where he looked at lamellar organization. So he looked all the way through a cornea to look at what is the preferential orientation of the lamellae, which each have a different orientation. And in a normal cornea at the top, the preferential orientation is vertical and horizontal. But in a keratoconic cornea, in the area of pathology, this is disrupted and is absent. And this is the area that's weakened, this focal area. It's also shown with beyond microscopy, published by Giuliano Scarcelli, where if you look at the keratoconic subject on the right, you can see there's asymmetry in the biomechanical properties as opposed to the normal subject on the left. Now, I want you to think of a balloon, as shown here, that you blow up, because there's more to stress distribution than thickness. There's also curvature. So everywhere inside this balloon, it has the same pressure. And yet, at that end, where the curvature is greatest, there's almost no wall tension. And that's the same thing in keratoconus. So let me show you what I mean. If you look at hoop stress, which is the circumferential stress for a spherical shell, it's the pressure times radius of curvature divided by twice the thickness. So it's a pretty simple formula. And if you look at what is going to make stress higher, certainly IOP is going to make it higher, but of the shape, a smaller thickness in the denominator makes that value bigger, and a flatter surface where you have a greater radius of curvature in the numerator, that also makes that larger. So what we did is define the corneal contribution to stress, which is just basically this dimensionless quantity of radius of curvature over twice the thickness. And it has the same relationships that the other one did, but I pulled out the confounding influence of intraocular pressure. Because if you include that, it is almost impossible to determine the stress distribution because you change that with changing pressure. We did a prospective observational study with 67 eyes of 41 subjects diagnosed with keratoconus. We used the Corviz, where if you have a stiffness parameter at first applanation and highest concavity and stress strain index, when those are higher, the stiffness is greater. And then the shape ones, the DA ratio, the ratio between the center and a peripheral point, it's opposite. That's lower has greater stiffness, because again, stiffness is resistance to deformation. So the higher these shape parameters are, the lower the stiffness. From Pennicam, we looked at a zonal value, and I don't have time today to talk about why you should not use a single point Kmax. And then also we used index we developed, excuse me, to look at the distance of the cone from the center. And if you look at this, the cone location magnitude index, it searches the entire cornea for this area of greatest curvature rather than taking the steepest point, which in keratoconus may have artifact, and then taking the zone around it. And you can also do that same approach and look for a minimum value instead of a maximum value, and that's what we use on thickness. And so we looked at, in that population, we compared to 147 normal eyes, and we have the pachymetry map on the left, average of all. Anterior tangential, it is very important to choose tangential rather than axial. And then the stress map, the corneal contribution to stress. And what you can see in these normal eyes, that the thinnest area of all of them is near the center, as we expect. That's also where the curvature tends to be the greatest, but there's not a great differential in curvature. And that's also here where the stress is actually the highest. So you have higher stress where it's thinner. And that shows you in normal eyes, the stress distribution is dominated by thickness. But if you look at the 57 keratoconic eyes with central cones, again, thinnest, greatest curvature, that's not highest stress anymore. It's lowest, it's minimum. So you have minimum stress where the cornea is thin. In keratoconus, there's an evolution of this stress distribution such that it doesn't behave the way a normal cornea does. And it's the same thing with eccentric cones, where you have the thinnest area, the greatest curvature, and minimum stress. So what we did is did a regression of the distance of minimum pachymetry to this highest stress. And what you can see, it doesn't change in the normal eyes, but in the keratoconic eyes, as that curvature gets greater and greater, the maximum stress moves farther and farther away from the thinnest spot. We published this in 2023, so a couple of years ago. Now, this is the important thing. In this same population, we define central, can you put that slide back on? It's a very important slide. This tells you why you need to use the tangential algorithm, because the axial algorithm is a running average from the center to the periphery. So if you're screening for keratoconus, you want big features, you use the axial algorithm. But if you're evaluating the response to cross-linking, you need to use tangential, because in this population, if we use axial, we have an even distribution between central and eccentric cones. But if you use tangential, only 9 subjects had eccentric keratoconus. Most of them are central. And I think that you'll find that in more populations than this one. This just shows that both of these regressions show that the farther away the cone is from the center, the steeper is the central curvature. And this shows, even with a complicated finite element analysis, the area of greatest curvature is actually the minimum stress. So the take-home message, in keratoconus, thinnest spot is not highest stress. Continual change in the stress distribution causes the evolution from thickness to curvature driven, and the location of the cone impacts the measurement that you're going to make with a biomechanical device. Thank you.